exact equations. So this is another type of differential equation. So first of all, we need to review something we have learned in calculus class. If we have a function with two variables, z is a function of x and y. So for example, we can have a z equals x squared minus 5xy plus y cubed. So if we only have one variable, usually our function look like this: y equals something of x, for example, x squared. So this function only has one variable. In this function, we have two variables, two independent variables. So we use z to denote the dependent variable. Okay, so if we take the derivative, because we have two independent variables, we need to specify. We take the derivative with respect to which variable. So what we write is usually partial z over partial x. So that's called a partial derivative. And to take the derivative, we consider x as an independent variable, and we can treat y like a number, like a constant. So if we take the derivative of this function, the derivative of x squared is 2x, and the derivative of negative 5xy, remember to treat y as a number. So if we rewrite it, maybe this will look better. So if we consider negative 5y as the coefficient and y is the variable, so when we take derivative with respect to x, it's just going to be the coefficient. So it's kind of like if you take the derivative of negative 5x, that would, with respect to x, that would be just negative 5, the coefficient of negative 5, because the derivative of x is 1, right? So the same thing here. We treat x as a number, so we get negative 5y. So with respect to y, you get negative 5y. Derivative of x is 1. Okay, now plus the derivative of y cubed with respect to x, because y is considered as a number, constant. So the derivative of any constant is 0. Okay, so this is the partial derivative of z with respect to x. So it's just the 2x minus 5y. Similarly, we can do partial derivative with respect to y. Now, this time we will treat y as the variable, but we will treat x as a constant. Okay, so when we take derivative of x squared, that will be 0, because it's a constant. And now derivative with respect to y, so we will get negative 5x. And derivative of y cubed will be 3y squared by the formula. So it's negative 5x plus 3y squared. And this is the partial derivative of the function. And there's the differential. So what would be the differential? When we have a one variable function, differential is like dy equals 2x times dx. Okay, so this is called a differential, dy. dy over dx is the derivative. The differential dy is called a differential. Okay, so we have the differential for one variable function. It's the derivative times dx. What about two variable functions? So follow the formula we learned before. It's going to be dz equals the partial derivative with respect to x times dx plus partial derivative with respect to y times dy. So this is the differential for the two variable function. So if we plug it in to the formula, dz in this example will be partial derivative with respect to x. So partial z over partial x, that's going to be 2x minus 5y times dx plus partial z over partial y, that's negative 5x plus 3y squared, right here, times dy. So this is the differential. Okay, so it looks like something times some function times dx plus another function times dy. So that kind of gives us another method of solving a differential equation. We will treat the left side, for example, if I have something like this, 2x minus 5y times dx plus negative 5x plus 3y squared dy equals 0. So that's exactly the differential of z, the left side of the equation. Notice this equation is still first order. It doesn't look like we have the derivative in there, but if we divide dx both sides, so if I divide dx both sides, we will get 2x minus 5y. Dx over dx is 1. Plus negative 5x plus 3y squared times dy over dx equals 0 divided by dx is 0. So if we divide dx both sides, this is the derivative here, and it's the first order. But notice this is not linear because the power of y is 2, and if we multiply the power, actually it's not linear. So this is not linear. But it is first order. So in chapter 2, we only talk about the first order differential equations. We have the linear case, first order linear, and this one may not be linear. So how do we solve this one? By the example, the differential formula, we notice the left side is exactly, so we treat it like the differential of two variable function. So I can write it as d. What is z? Z is x squared minus 5xy plus y cubed. How did I find this out? We will explain this later. But from this example, we know, because that's how I got my differential dz, right? So I know it's z should be x squared minus 5xy plus y cubed. So that replaces z with the function, two variable function. So that's the left side. Okay, now equals 0. Okay, so now we can integrate both sides. The left side will be x squared minus 5xy plus y cubed, and the right side is the constant c. Okay, so that's the solution, where we get an implicit solution this time, and it's kind of difficult to solve for y, so we will just leave it as it is. Which is called an exact equation. Because the left side is an exact differential of some two variable function. Because sometimes the left side may not be a differential of a function, a two variable function. So in that case, we won't be able to use this method. So what is the criteria for the left side to be exact differential? So criteria for exact differential of a two variable function. Well, okay, so what we need to check is, so if I call the coefficient function of dx, we call it m. So that is the function in front of dx. If you look at this example 1, so the function in front of dx is 2x minus 5y. That's our m function. And we call the function in front of y n. Okay, so that's the left side. So in this case, this is our m function, this is n function. So what we need to check is to make sure the partial derivative of m with respect to y equals the partial derivative of n with respect to x. So this is the criteria. So for example, we can verify example 1 is an exact equation by this criteria. So I'm going to work out partial m with respect to partial m over partial y, so equals remember, we take the derivative with respect to y. That means y is a variable, but x is constant. So the constant, 2 is constant, x is constant, so we get 0. Derivative of 2x is 0. And the derivative of negative 5y is negative 5, so we get negative 5. And we take the partial derivative of the other second function with respect to x, so we get negative 5 and plus 0. And you can see they're equal to each other. So we get a partial m, partial y equals partial n equal over partial y. So that makes the example 1 an exact equation. So if it is an exact equation, that guarantees the left side to be a total differential. A total differential. So it's a differential of some two variable function. And then we can integrate both sides. Okay, so let's look at, we're going to skip the proof here, why this is a necessity. So why a function satisfying this condition must be exact differential. So we're going to look at an example